What kind of math do computers use? You may have heard that computers run on some sort of math. And even the name computer has the word compute in it, which means to determine by mathematics. But what kind of mathematics could play chess, show high-quality educational videos, or execute arbitrary computer code? That would be discrete mathematics. This is different from the mathematics you may have learned in grade school. For example, let's look at the number 4. In grade school, 4 means 4 of something. 4 coins, 4 corners, 4 students. In discrete mathematics, 4 does still represent this value, but we also want to consider its properties and how it's similar and different from other numbers. You've already used the properties of numbers in your everyday life. Even numbers are great because we can divide them by 2 and still have a whole number. It makes sharing between friend groups of size 2, 4, 6, etc. easy as pie. Meanwhile, odd numbers can never be split into 2 groups evenly. It doesn't matter if you have 1, 3, 5, or 7. Here you can see how each number or element is its own individual thing. Look at those little guys go. What's great about properties is it lets us make rules about all numbers. So even if we have a beast of a number like this, we can still say that it's an even number and will obey the same properties of other even numbers. Now that we have an idea of what properties of numbers are, let's organize our numbers into a set. When organizing numbers, you're probably familiar with the number line, or the Cartesian plane, which is really just 2 number lines perpendicular to each other. In discrete math, we can use sets to help us organize our numbers in the same way. We separate our elements with commas to make them easier to read. Next, we'll put some curly brackets around them to indicate that this is a set of numbers. Finally, we'll use a capital letter for a name. This is a set, and it is a fundamental building block of discrete math, just as important as the numeral is to arithmetic or the sine function to geometry. We discussed how, in discrete math, numbers have properties. Well, sets also have properties, and many of which are similar to what you already know. In your arithmetic class, you know that when adding or multiplying numbers, order doesn't matter. Sets follow this same pattern. A set of students, like Alice, Bob, and Eve, is the same as Bob, Alice, and Eve, which is the same as Eve, Alice, and Bob. Another arithmetic concept you should be familiar with is that sometimes problems can simplify. If you add 0 or multiply by 1, you get the same value. Sets also have this, where if you have multiple elements that are identical, you can simply remove the duplicates. So, just like how 5 plus 0 is 5, and 12 multiplied by 1 is 12, the set 1, 2, 3, 2, 1 is just the set 1, 2, 3. This is important because when we have a finite number of elements in a set, we often want to know how many. This is called the cardinality of the set, and we use pipe characters, which you might recognize as similar to the absolute value. We observed that sets can have multiple values, and we care about whether an element does or does not belong to a set. To formally write this, we use a stylized epsilon, which denotes that an element is in a set, and the same symbol with a line through it to show an element is not in the set. Another thing you should be familiar with from your schooling is algebra. In algebra, you use symbols like x to represent numbers. Discrete math also uses symbols like x and other lowercase letters to represent elements in a set. Remember, in discrete math, we often care more about the set itself than individual elements. So we don't want to develop a rule about the number 4. We want to develop rules that apply to all even numbers. So if we have a set of even numbers, we'll use x to denote any even number you can think of, and even the ones you can't think of. When writing infinite sets, we can use the propositional function notation, which is the set of all elements x, where x is true in the proposition p of x. P of x could be x is even, x is prime, or x is less than 8. When you see this format, don't be confused. It's just another way to write a set. Some sets come up frequently and have special notation. Let's take a look at some of them. We have the counting numbers, which are 1 through infinity, the natural numbers, which are 0 through infinity, the set of all integers, which is negative infinity through infinity. All of these sets are whole numbers. To cover fractions, we have the set of real numbers, which is any number that can be found on a number line, whether whole, a fraction, or even an irrational number. We also have the empty set, which is a set that contains no elements. Now, you might have noticed that some of these sets seem to contain all the elements of the other set, like how the natural numbers contain all the counting numbers plus 0. We call this relation of smaller sets to bigger sets subsets, and it occurs when a set is completely contained within another set. We write this using the subset symbol, which is analogous to arithmetic's less than symbol. There is also a superset symbol, which is just like the greater than symbol. You can use the same trick, imagining an alligator eating the larger number or the larger set. If a set isn't a subset because it contains values that aren't in the other set, we write the subset symbol with a line through it to show that one set is not a subset of the other. The relation can be difficult to picture at first, so we'll visualize them with Venn diagrams. In this first Venn diagram, we can see the counting numbers are a small circle within a larger circle that represents the natural numbers. The box around the Venn diagram represents the universal set, which contains every element that is relevant to a particular problem. So in a problem with all integers, -1 is in the universal set, while non-integer numbers like pi or the square root of 2 are outside the set. This set is always present, even if we don't draw it, and it is contextual to the problem. Next, let's look at the set of the first 4 prime numbers and the set of the first 4 positive even integers. They both share the value 2, but they also have different values. So we say the first set is not a subset of the second set. And here's how it looks as a Venn diagram. As we said, sets are like numbers. They're fundamental building blocks of discrete math. Also like numbers, they're more useful when combined with their fellows. We call these combinations set operations. Just like how arithmetic has addition, subtraction, multiplication, and division, sets have unions, intersections, complements, and the symmetric difference. Unions are the combination of sets. Formally, they're defined as A union B is equal to the set of all x, where x is an element in A, or x is an element in B. So if we use A and B from our earlier example, then A union B is the set 2, 3, 4, 5, 6, 7, and 8, which we can represent by shading in the entire Venn diagram. Intersections are the shared elements between two sets. Formally, They are defined as the set of all x, where x is an element of A and x is an element of B. So once again, using our earlier example, the set defined by the intersection of A and B is simply the set containing 2, which we can represent by shading in the parts of the Venn diagram that overlap. Now say we have a set C, which is the set 10, 11, and 12. This has no overlap with either A or B, so if we calculate the intersection, we get the empty set. When this happens, we say the sets are disjoint sets. The complement of a set is the set of elements unique to one set. This is quite similar to how the negative numbers work. Formally, the complement is defined as the set of all x where x is in set A and not in set B. So in our example, the complement of set A with respect to B is 3, 5, 7, which we can represent by highlighting the part of the Venn diagram that is only A and shares no overlap with B. Sometimes, we care about all elements not in a set, so we use a slightly different notation, where we write a line above the set to denote that it's a complement. This is how we would write the set of all elements not in A. The symmetric difference is the set of elements not shared by either set. Formally, this is the set of all x where x is an element of A and not an element of B, or x is an element of B and not an element of A. So if we calculate the symmetric difference of A and B, we get the set of all numbers except 2, because 2 occurs in both sets A and B. Those are some of the most common set operations, and much like how arithmetic operations have certain properties, like PEMDAS, or that any whole number multiplied by 2 will be even, set operations also have properties, many of which have similarities to your basic math class. Unions, intersections, and the symmetric difference are all commutative. Order does not matter for these operations, and because order doesn't matter, we can associate the operations any way we please. It doesn't matter if we do A union B union C, or B union C union A. Both give us the same filled-in Venn diagram. Unions and intersections are distributive. So, a set A intersecting the union of B and C is the same as the intersection of sets A and B unioned with the intersections of A and C. Similarly, set A unioned with the intersection of sets B and C is identical to the union of sets A and B intersected with the union of the sets A and C. Unions, intersections, and the symmetric difference are idempotent. That is to say, applying the operation to the same set will return the same set. So A union A, or A intersect A, will return set A. This is different from the complement, which is an involution, meaning the same operation applied twice will return to the original set. If we create a union of a set with its complement, we get the universal set. This is because we can think of the complement of a set as everything that isn't in the set. So every element that isn't in the set, unioned with every element in the set, is every possible element, i.e. the universal set. Similarly, if we create an intersection of a set with its complement, we get the empty set. This is because we're trying to find the common ground for every element in a set and every element not in a set. This can be extended to the universal set and the empty set. The complement of the empty set is the universal set, and the complement of the universal set is the empty set. Complements, have a unique version of distribution called De Morgan's laws. So if we try to take the complement of the union of sets A and B, we can instead calculate the intersection of the complement of A and the complement of B. Likewise, if we want to take the complement of the intersection of A and B, we can instead take the union of the complement of A and the complement of B. Let's end this video looking at a practical example of how we can use sets to calculate survey responses. Let's look at a pretend survey where we asked people if they want apples for a snack or bananas. Now recall that the cardinality of a set refers to the number of elements in a set. If we have a simple A or B question, and the people taking the survey can only choose one option, then we can simply add the set of people who chose apples and the set of people who chose bananas together. Pretty straightforward. Now let's say, instead of asking the people to choose one or the other, we simply ask if they like apples, or bananas, or both. We'll say person A voted for apples and person B voted for bananas, and when we tally up our surveys, we get the apples set and the bananas set. So the cardinality of the apples set is 5, and the cardinality of the bananas set is 6. However, we know that there are some people who voted for both, so we subtract the cardinality of the intersection, which is the set CE, giving us 2. So we know that there are 9 unique voters. More generally, this is the formula: the cardinality of A plus the cardinality of B minus the intersection of A and B, which gives us the total cardinality of the union of sets A and B. For a survey of 9 people with 2 options, this is a fairly trivial calculation. But if we scale it up to 3 options, then we not only have to account for the intersections, but we have to account for the intersection of intersections. Let's imagine a new survey. This time, the snacks are apples, bananas, or cantaloupe. We count up the votes and find that apples got 70 votes total, including overlap, bananas got 60, and cantaloupe only got 35. Apples and bananas got 20, apples and cantaloupes got 5, and bananas and cantaloupes got 10. There were also 5 people who said they wanted any of the snacks. So first, we add the cardinalities of each fruit. Then, we subtract the intersections. Finally, we add back the intersection of the intersections. So with nothing but the totals of the survey results, we can say that 135 unique people answered our survey. This sort of calculation is frequently used in databases, which is how most businesses, governments, and websites store their data. And it's just the tip of the iceberg when it comes to the practical uses of discrete math. Discrete mathematics is the basis of all digital technology you encounter in your everyday life. You're still a long way from understanding all the math that goes into a computer. Nevertheless, I want to congratulate you on taking the first step with discrete mathematics.